The first sign won't be an explosion or a siren or even a visible flash in most cases. It will be silence, machines halting mid-process, screens going dark, vehicles stalling in places they were never meant to stop, elevators freeze between floors, air traffic control systems go blind, and across entire regions, the electrical grid collapses in a fraction of a second. This is the realistic onset of a high-altitude electromagnetic pulse event, commonly referred to as an EMP. It is not cinematic destruction, it is systemic interruption. And what makes it dangerous is not what you see, but what quietly stops working all at once. To understand why this happens, you have to look at how modern electronics are built. Nearly every system that defines daily life, communication networks, power distribution, water treatment, transportation logistics, relies on microelectronics. These are highly efficient, densely packed semiconductor circuits designed to operate at extremely low voltages. That efficiency is their strength in normal conditions, but under an EMP, it becomes a vulnerability. An electromagnetic pulse introduces a sudden surge of energy into the environment, inducing high voltages in conductors like power lines, antennas, and even the wiring inside devices. These voltages exceed the tolerance of microcircuits almost instantly, causing irreversible damage. A common misunderstanding is that an EMP behaves like a blast wave, affecting only the immediate area of detonation. In reality, a high-altitude EMP can impact an area the size of a continent. This is because the pulse interacts with the Earth's magnetic field, spreading energy across vast distances. The event itself is typically divided into three components: E1, E2, and E3. The E1 phase is the fastest and most damaging to electronics, occurring in nanoseconds. The E2 phase is similar to lightning, which most systems are somewhat protected against. The E3 phase is slower, but far-reaching, capable of damaging large-scale infrastructure like power grids through geomagnetic induction. What is often overlooked is how interconnected these systems are. The electrical grid is not a series of isolated components. It is a synchronized network that depends on precise timing and balance. When an EMP disrupts this balance, it can trigger cascading failures. Transformers, which are critical for stepping voltage up or down, are particularly vulnerable during the E3 phase. These are not easily replaceable components. Many are custom-built, weigh hundreds of tons, and require months or even years to manufacture and deliver. Once they fail, restoration is not immediate. It becomes a long-term crisis. Evidence for this vulnerability is not theoretical. Historical data from solar storms, particularly the Carrington event of 1859 and the Quebec Blackout of 1989, demonstrates how geomagnetic disturbances can induce currents in power lines and disable transformers. While those events were natural and less intense than a nuclear EMP's E1 phase, they still caused significant disruption. Modern infrastructure, far more dependent on sensitive electronics, would likely experience more severe consequences under similar or stronger conditions. The survival implications begin at a level most people underestimate. When the grid fails, water systems are among the first to degrade. Municipal water relies on electrically powered pumps to maintain pressure and distribute clean water. Without power, pressure drops and contamination risks increase. Wastewater systems also fail, leading to sanitation issues that can escalate into public health crises. Food supply chains, which depend on refrigeration, transportation, and digital logistics, begin to break down within days. Fuel distribution halts, as pumps at gas stations require electricity, and refineries cannot operate without stable power. This leads to a second layer of escalation that is often ignored: communication collapse. Most modern communication systems, cell towers, internet infrastructure, satellite ground stations, depend on both power and functioning electronics. While some systems have backup generators, these are limited by fuel availability and maintenance constraints. Once communication fails, coordination becomes nearly impossible. Emergency response systems lose the ability to deploy resources effectively, and individuals are left without reliable information. There's also a persistent belief that personal electronics, if turned off, are safe from EMP effects. This is only partially true and depends heavily on the device's exposure and design.
Small, unplugged devices with minimal wiring may survive, but anything connected to long conductors, such as power cords or antennas, is at significantly higher risk. The induced voltage from an EMP travels along these conductors, effectively delivering the pulse directly into the device's internal circuitry. Hidden within this is a critical piece of science that is rarely discussed in practical terms: shielding effectiveness. The concept of a Faraday cage is often mentioned, but rarely understood correctly. A true Faraday cage works by redistributing electromagnetic energy around its exterior, preventing it from penetrating the dakhel. However, the effectiveness depends on continuity, grounding, and the absence of gaps. Even small openings can allow high-frequency components of an EMP to penetrate and damage the contents. This means that improvised solutions, while potentially helpful, are not guaranteed to provide complete protection. Empirical testing conducted by various engineering groups and government agencies has shown that shielding can significantly reduce damage, but only when implemented correctly. This includes using conductive enclosures with proper sealing, avoiding direct contact between the protected device and the enclosure, and ensuring that the enclosure itself does not act as an antenna. These are not intuitive design principles, and they highlight the gap between theoretical knowledge and practical preparedness. From a survival perspective, this translates into a shift in priorities. It is not enough to have supplies. You must have systems that function without reliance on vulnerable infrastructure. This includes alternative methods for water purification, such as gravity filtration and chemical treatment, which do not require electricity. It includes mechanical tools and analog backups for critical tasks. It also involves understanding how to maintain and repair equipment without access to digital diagnostics or replacement parts. As the situation evolves, the focus moves from immediate impact to sustained resilience. The first 72 hours are defined by confusion and rapid resource depletion. After that, the challenge becomes long-term adaptation. Communities that can organize, share resources, and establish local systems of production and distribution are more likely to stabilize. Those that remain dependent on external support face increasing risk as time progresses. This progression leads to a deeper question about modern dependency. The systems that provide convenience and efficiency also create fragility. An EMP does not introduce new problems. It exposes existing ones by removing the infrastructure that conceals them. Understanding this is essential for effective preparation because it shifts the mindset from reacting to an event to anticipating systemic failure. And as the layers of disruption continue to unfold, another critical factor emerges, one that determines not just survival, but the ability to recover in a world where the grid may not come back anytime soon.